Hey folks, today we're going to talk about telescoping series, which is an additional interesting topic in sequences and series. They're a little different than geometric, they're a little different than arithmetic. They are pretty neat, and we will see why they're called telescoping series, and we'll see how we can handle them. So let's go ahead and get started. Now, if you look at something like this, that was a really long, awkward pause. But if you look at something like this, you probably look at this and you're like, well, I have no idea how to get started. And when you look at something like this and you have no idea how to get started, it's typically a good idea to just start listing some terms and see if that helps you. Maybe it will, maybe it won't. But let's just list a couple just to see, in the off chance that it does help us. So let's start listing a couple terms. Notice we're starting with n equals 3. So let's list our first term, which would be 10 over 3 squared. I'll just write as 9 plus 3. Then we'd add to that our second term, which would be 10 over 4 squared is 16 plus 4. Let's go ahead and list one more. 10 over, when n is 5 now, we'd have 25 plus 5. So we've got 10 over 12 plus 10 over 20 plus 10 over 30 plus yada yada yada. I'm not really seeing a very useful pattern here that I can use. It's definitely not arithmetic, it's definitely not geometric, and that's really all we've talked about so far. And so we're going to need to come up with a different approach to this problem. And the approach that we're going to use is something called partial fraction expansion, also known as partial fraction decomposition. And the idea is basically the opposite of finding a common denominator. The idea is we want to take this expression right there, our explicit formula, and we want to split that up into the sum of a couple separate fractions. And there's a specific technique we can employ to do so. And the first thing we want to do is we want to factor that denominator. So let's ignore the sum, let's ignore all of that. Let's just look at this as a fraction, 10 divided by n squared plus n. Now the first thing I'm going to do is I'm going to factor the denominator. So 10 over n squared plus n, I can factor out an n from both of those terms, and I'm left with n plus 1. So I have 10 divided by n times n plus 1. And now the idea here is we will split this up into the sum of two different fractions. One fraction will have the denominator of one of the factors, and the other fraction will have a denominator of the other factor. Now I don't know what goes on the top of either of those fractions, so when you don't know what something is in math, you typically just let some variable stand in its place until you do know what it is. So I'm making the claim that I can rewrite 10 over n times n plus 1 as two separate fractions, one denominator with n, one denominator with n plus 1. And again, I don't know what those numerators will be, but I want to figure out what those numerators are. That's my goal here. And in the process of figuring out what those numerators are, I'm going to do something that might seem kind of counterintuitive. I'm going to smush these fractions back together. What I mean is I want to find a common denominator between them, and so I can then write them as a single fraction again, which again probably seems silly, but when we go through this process, hopefully you will see how that ultimately helps us. So, in order to do so, I'm going to spread these terms out a little bit. In order to write these together, I need to find a common denominator. And the easiest common denominator to find would be the common denominator that I started with, that n times n plus 1. Which means, in this first fraction, I need to multiply by n plus 1. But if I do that in the bottom, I need to do it in the top as well. And in the second one, I have that factor of n plus 1, and I need a factor of n, but if I do it in the bottom, I need to do it in the top. So now I have two fractions here with the same denominator, which means I can rewrite them as a single fraction. So I have a times n plus 1 plus b times n all over n times n plus 1. And again, it probably seems silly that we separated and then smushed them back together, but now we need to focus on this piece right there and this piece right there, what we started with and what we now have. Because notice that these two fractions, or rather, let me show you this one. Let's focus on these two, because those denominators look the same. It was the same in the previous one too, but these look the same, so it's easier to see. But the idea is these two are equivalent, and again, that's only true because we don't yet know what A and B is. We're saying some A and some B will make this true, and we want to figure out what A and what B make this true. But the key here is both of these fractions have the same denominator, which means the numerators also have to be equal to each other. And so I have the equality 10 equals A times n plus 1 plus B times n. So I have this equality here. Now, there are multiple ways you can go about trying to solve this. One way is coming up with a system. The systems typically aren't very complicated, but another way is to substitute in some values of n that will make this easy to solve. Now, since we're saying this is an equality, and we're looking at pretty much all n values there, the idea is this should work for any values of n. And if we want this to work for any values of n, then let's choose some values of n that will make our lives easier. For example, let's choose, now I'm just focusing on this bit, let's choose the n value of 0. And let's plug n equals 0 into this equation, and we'll see what happens. So if n equals 0, on the left I just have 10, and on the right I have a times 0 plus 1 plus b times 0. And b times 0 is 0, so that goes away. And I'm left with 10 equals a times 0 plus 1 is 1. So I just have 10 equals a, which is kind of nice. 10 equals a. Okay, that's cool. What else can we tell? What other n value would be a smart choice? Well, how about the n value of negative 1? Because if n equals negative 1, then I can rewrite my equation, and I'll get 10 equals a times negative 1 plus positive 1 is 0. Now that term's gone, plus b times my n value, which was negative 1. So simplifying this, I have 10 equals negative b, and so b equals negative 10. So I've found a, and I've found b. But what does that mean? All right, we'll jump back up to where we were. So look at this middle step right there. In this middle step, again, I found a common denominator, but before I started that, I didn't have that n plus 1 there, and I didn't have those n's there. I just had this fraction a over n plus b over n plus 1. And now I found a and I've found b. So I'm going to plug this in. A we found to be 10, so when I have 10 divided by n, I would have plus b is negative 10 divided by n plus 1. But instead of writing plus a negative 10 like that, I'm just going to write it as minus 10 over n plus 1. And what we're saying is that this right here is equivalent to what we started with. That equals 10 over n times n plus 1. And since this is the first time we're doing it, let's actually verify that. Let's make sure that this did indeed work the way we wanted it to. If we wanted this to work in that manner, let's go ahead and take this expression, 10 over n minus 10 over n plus 1, and let's find a common denominator, and let's put it all back together. So again, if I find a common denominator, I'm multiplying this first one by n plus 1 in the bottom and the top, and I'm multiplying the second one by n, because now I have a common denominator, and I can smush them together. So what do we have in the numerator? Well, in the numerator, I have 10. I'm going to distribute that in, so I'm going to have 10n plus 10, minus, on the right, I just have 10n. This is all over n plus 1 times n. Keep simplifying. What do we have? Well, we have a positive 10n and a negative 10n. So this simplifies down to 10 over, and I can multiply that n in if I want, n squared plus n, which is what we started with, 10 over n squared plus n. So we have indeed found the partial fraction expansion of this term, of this fraction, but who cares? What was the point of that? Well, now we need to jump up top. We have just found an equivalent expression for this fraction, 10 over n squared plus n. So let's use that equivalent expression. N equals 3 up to infinity. And we're saying that we have an equivalence, 10 divided by what we found down here in the box, right there, 10 over n minus 10 over n plus 1. So, since we found those two fractions to be equivalent, these two sums need to also be equivalent. And you're probably looking at that and you're probably thinking, well, that doesn't look any easier. But it is, I assure you. It is actually pretty nice. So let's go back to our first approach, which was, if we don't know what this looks like, let's start listing some terms. And so let's start with our first term when n equals 3, because that's where we are told to start. And if I list these terms out, I need to plug into both of those fractions now. So I'll get 10 over 3 for my first one, then minus 10 over 3 plus 1 is 4. All right. So there's my two terms now, my two fractions coming from my first n value. And now let's do the next one. When n equals 4, let's plug into both fractions now. We'll be adding this second part of the sum. 10 over n is 10 over 4, minus 10 over n plus 1 would be 5. And let's do one more just for fun, plus n equals 5. We'll do two terms again. It's going to give me 10 over 5 minus 10 over 6. And notice what's happening in each set here. The second part of the second part of the term, what am I trying to say? Look at n equals 3. The second part of that term is canceling with the first part of the next term. And so those are gone. And then similarly, the second part of n equals 4 is canceling with the first part of n equals 5. And this pattern is going to continue on forever. If I did n equals 6, I would get a plus 10 over 6 minus 10 over 7. And those right there would cancel. And if I did n equals 7, then that negative 10 over 7 would cancel. So the only thing that's not going to be canceled is this very first term right there, 10 thirds, which means that this sum is 10 thirds. That's nuts. It blows my mind that you can do that. These are called telescoping series because, like a collapsible telescope, you can expand them out, but then you can smoosh them back down and simplify them down to just often a single term, sometimes a couple terms added together. But that's the basics of how it works. What I'm going to now do is show you a few other problems and just simply tell you what the answer is, and I want you to try and work through a solution on that. Some of them are easier than others, but you have me in class to help with them, so here you go. Here's your next one. Same idea there. Factor the denominator, pull it apart, figure out what each numerator should be by plugging in some good values for n, and then figure out what cancels. And when you get down to it, you should find that this sum is going to be equal to 8 thirds. So practice that one. Then this next one right here, again, it's the same idea, factor the denominator, split it up, and you will find that this sum here is equal to just 1 third. Couple more here for you. This one is going to be equal to, again, 10 thirds. Make sure you can get there. And then finally, this last one right here. I don't know why I said this last one. It's not actually the last one. But this one right here is going to equal 1/2. But again, the point is now you need to try and get there. This last one right here is the trickiest of them. But they're all going to work in the same way. You start by factoring the denominator, do my little pointer, start by factoring the denominator, and then split it up into two fractions, one with each denominator, put an A over B. I'm sorry, an A in one and a B in the other. Find a common denominator, smush them together to get that expression. Set the numerator equal to the numerator you started with. Then plug in some good values for n that will make pieces simplify. Find your A, find your B, find your partial fraction expansion, and start listing some terms until you find a pattern of what cancels out. Now the next thing I'm going to show you is one step beyond this. If you're ready for it, give it a shot. If you're not, well, this is going to be a bonus question on your final, so it might be worth putting the time in to try and learn it. So let's go ahead and do this real quick. Again, this one, we're just finding the partial fraction expansion, no sum or anything like that. The idea is exactly the same. We want to start by factoring the denominator. So in this denominator, notice that we have an x squared in both terms that we can factor out. If you factor out an x squared from x cubed, you're left with x. If you factor out an x squared from x squared, you're left with 1. So there's our denominator factored. We're left with 2x squared plus x plus 2. Leave that in the top. And now let's do what we did before. Let's split this up. And so we're going to split it up into some fractions again. We'll put one of the factors as one denominator, and we'll put the other factor as the other denominator. And I would put an A there. Let's put a plus between them. But here's where this problem differs from the others. If you have a repeated factor in the denominator like that, what I mean is a factor that has a multiplicity other than 1. This has a multiplicity of 2. If that's the case, you need to actually add another fraction with just one lower denominator, just the x. So for example, if I had something that had a factor of x plus 1 cubed in the bottom, like that, something over x plus 1 cubed, if I'm splitting this up, I'd be doing one denominator of x plus 1 cubed, I'd be doing one denominator of x plus 1 squared, and I'd be doing a third denominator of x plus 1. However many powers it has, 3, you need to keep going until you have one of each power. So since we had x squared, we need an x squared, and we also need a denominator of x. I'm not going to give you anything more than just a double multiplicity like that. So if it's squared, you need to have one with it squared and one without it. So we'll put a b over that and a c over that. Alrighty. At this point, the idea is exactly the same. We need to now find a common denominator. So I'm going to give myself a little more space here. I'm going to spread this out a bit, move this over to the middle like that. Now, I'm finding a common denominator, which is going to be the denominator I started with, x plus 1 times x squared. And that means in this first fraction, I need a power of x squared. So I'll put one on the bottom and one on the top. And in this section fraction, I have an x squared and I need an x plus 1. So put one in the bottom and one in the top. Now in this third one, I need an x plus 1, but I also need an x to get x squared. So I need to not only have my x plus 1, I also need to have an x there. And now we can smush these fractions together, so I will have a x squared plus b times x plus 1 plus c times x plus 1 times x, and this is all over x plus 1 times x squared. Pardon my belch, that was disgusting. I'm gross, I apologize. And now, again, the claim is this is equal to what we started with, 2x squared plus x plus 2 over that denominator x squared times x plus 1, which is just the factored version of x cubed plus x squared. Now, since these denominators are equal to each other, and these two fractions are equal to each other, we know that the numerator has to be equal to the other numerator. So we have 2x squared plus x plus 2 equals ax squared plus b times x plus 1 plus c times x plus 1 times x. Now at this point our approach to this problem is going to be the same as our approach to that first problem, with one key difference in the end. I want to plug in some x values that will make this math simple and make a lot of things cancel each other out. So think about what x values you could plug in that would get those x expressions to go to 0 and get rid of either an a, a b, or a b and a c, or a c and an a if possible. So one good one to choose would be x equals 0. If I plug in x equals 0, let's see what equation we get. Well, I get 2 times 0 squared plus 0 plus 2 equals a times 0 squared plus b times 0 plus 1 plus c times 0 plus 1 times 0. Let's go through and simplify things. That is 0. Well, that's 0 also. So on the left, I'm just left with 2 equals a times 0 squared is 0 plus b times 0 plus 1 is just b. And then c times 0 plus 1 would be c, but I have that times 0 there as well. And so that term is gone, and I'm just left with 2 equals b. So we know that 2 is b. That's pretty good, or b is 2 rather. What's another good number I could choose to plug in? Well, if I plugged in -1, I would cancel out that x plus 1 bit. So let's choose x equals -1. And again, we can choose these values because we want this fraction to be equivalent for any x value. So let's choose these x values that make our lives easy. And so plug in -1, we get 2 times -1 squared plus -1 plus 2 equals a times -1 squared plus b times -1 plus 1 plus c times -1 plus 1 times -1. Let's simplify what we can. -1 squared is +1, so that first term is just 2, minus 1 plus 2 equals -1 quantity squared, again, is 1, so I'm left with an a, plus b times -1 plus 1 is 0, so that's gone. C times -1 plus 1 is 0, so that's gone. So all I have then is a equals that left side. 2 plus 2 is 4, minus 1 is 3, has to be my value for a. So I know a, I know b, and now I need to find c. Not quite as easy because I'm not going to be able to plug something in that cancels my a and b terms because c shares a factor with each of those, x plus 1 or x. But we could plug in another x value that would be at least easy for us to calculate with. So I'm going to plug in the x value. I should use a different color. Let's do the x value of 1, because positive 1 is typically a fairly easy number to work with. And let's write our equation. 2 times 1 squared plus 1 plus 2 equals a, which we know is 3, times 1 squared, plus b, which we know is 2, times 1 plus 1, plus c times 1 plus 1 times 1. And let's simplify things. On the left, I have 2 times 1 squared is 2, plus 1 plus 2, equals 3 times 1 squared is 3, plus 2 times 1 plus 1. Well, 1 plus 1 is 2, so 2 times 2 is 4, plus c times 1 plus 1 is 2. So 2c times 1 is still 2c. So let's move all the numbers to the left. So 2 plus 1 plus 2 is 5. So I've got the 5 there. I'm going to minus 3 plus 4 is 7. So let's subtract that 7 to the other side, and that will equal 2c, which means that -2 equals 2c. Sorry, I'm kind of all over the place here. Which means that c equals -1. So I found a, I found b, I've found c, which means I can go back up here to this red equation. Ignore the purple-blue stuff because that's just going to go away. I can use this red stuff now because I found A, I found B, I found C. So let's get a new color. Let's go a little magenta here. A is something. What is A? A is 3. So that first fraction is just going to become 3 over x plus 1. And what is B? b is 2. And so that will be plus 2 over x squared. And finally, c we just found to be negative 1. So I can write that last one as minus 1 over x. And this is the partial fraction expansion of what we started with right there. Those two pieces are equivalent. We have just found that relationship, which is pretty awesome. This is useful in calculus. You can do a lot of things in an easier way with the partial fraction expansion that you could not do as easily with something in a form like that. So there you have it. Again, this problem or a problem like this is going to be a bonus question on your final. So give it a shot.